Thank you very much for giving me this opportunity to present my article. Thanks for conference, thanks for UTB, thanks for professors and doctors for attending. My name is Khalid Abu Shahla. I'm from a PhD student. I'm a PhD student in Sakarya University of Applied Sciences. Also, I'm a researcher in the Biochem lab in our university, under supervision of Dr. Halil Arslan. He's my professor, and he's supporting me really even in this presentation. Let's start about the title of the article. It's a predictive modeling of radiation shielding properties for bioglass using machine learning. So I know it's a little bit complicated, so in the introduction I will explain some important principles and terminologies in this title. Let's start about the overflow of the presentation. We'll start about introduction. We speak about bioglass, radiation shielding, conventional tools that are used in radiation shielding field, AI radiation shielding, and current research and novelty. Then we'll speak about the materials and methods, results and discussion. Finally, we will conclude and give some recommendations out of our research. Let's start with the introduction. Simply, what's bioglass? Generally, when you think about bioglass, you think about a glass. But really, yes, it's a glass, but normally used inside the body, used inside the bones. But called glass because it contains a lot of silicon dioxide. So bioglass is a family of bioactive classes, primarily composed of silicon dioxide, sodium dioxide, calcium oxide, phosphorus pentoxide. Created by Larry Hench in the Vietnamese War. Why? Because they had a big problem in healing injuries of the soldiers. So he created a new materials, this bioglass, to help making the new implants more biocompatible and more effective, and it will be like forever inside the body, so it should be something biocompatible and efficient. Simply, it enhances the bone regeneration. Applications of this material, bioglass, in the bone grafts and implants, in coating on orthopedic and dental devices, and repair of cortical bone defects. Advantages, as I mentioned, biocompatibility, promotes bonding with bone, and reduces inflammation and promotes healing. The other section of our research, the radiation shielding, or medical radiation in general. Let's start with medical radiation. When we speak about medical radiation, we speak about a specific type of radiation, which is the ionizing radiation. Simply, the dangerous one. It's used in diagnostic imaging, like Röntgen and NCT, and in therapeutic procedures, like guns used in cancer healing and cancer cure. Importance, of course, it's important in diagnostic and therapeutics. Risks, it's simply dangerous because potential for radiation exposure, patients and healthcare professionals, and the most dangerous thing that it causes cancer somehow, destroys some DNAs, makes some mutations inside the body, and maybe cause to failure in other organs. So, because the radiation is important and dangerous, we have to use something to decrease the amount of exposure, which we call it in general radiation shielding. Radiation shielding generally considers, or the main fundamental of the radiation shielding, called ALARA. What does it mean, ALARA? You can see here, I'm sorry that I don't have pointer, but I will try to use something here. I know it's common. This is the ALARA. What does it mean, ALARA? As low as reasonably achievable. Means I will try to use radiation as low as I can, because a lot of radiation maybe will bring me a good results in therapy, maybe will bring a good images, but will make another causes and side effects. Maybe it will destroy the body. Maybe I will start with a small inflammation, I will end with cancer or in a failure in organs. So, to use that, we have three elements in ALARA. Limit of the time, increasing the distance, and using shielding. Limiting the time, decreasing the amount of time of exposure of radiation. Increasing the distance, be very, or not very far, but as far as possible from the source of radiation. That decreases the probability of being harmed, because it's stochastically causing the hazards. And finally, use the shielding, which is our topic. So what's radiation shielding? Involve using materials to minimize radiation exposure in medical settings. So it uses some materials to decrease the amount of exposure. Purpose: protects the patients and protects the doctors and technicians. It's quantified. This is a very important point because we built on this point. that generally when we compare between materials, we use something called mass attenuation coefficient. It's like a property used to compare between materials. This one will be better than the other one in radiation shielding, or in protecting or absorbing the radiation. So, also we have another parameters, not only mass attenuation coefficient, we have linear attenuation coefficient, the original idea of mass attenuation coefficient, half value layer, 10th value layer, effective atomic number, and mean free path. But we will focus on mass attenuation coefficient because it's the most common in the literature and most effective one, because it considers the thickness of the material, as you can see here, and the density of materials. And we speak about density, so it will not consider the concrete as a concrete, not as a thickness, and will consider the iron as an iron with thickness, not only as a thickness of iron. So, generally, mass attenuation coefficient can quantify how easily a material can attenuate, means reduce, radiation, and as it passes through. So, as you can see here in the image, IO is the main radiation, and I is the radiation after the shielding. So you can see it's lighter now, so it's less intense. Means it's safer. Maybe it will be still dangerous, but it's safer than the previous one. Simply higher MAC means indicates that better radiation shielding, a very important point. Mass attenuation coefficient allows for comparison for different materials, as we mentioned. We use it a lot with medical radiation. Now, I'm not speaking about all types of radiation. It's worse, of course, for all types of radiation, but now we are speaking about energies generally for medical applications, not for nuclear powers or for nuclear plants. Conventionally, we used a lot of tools for those types of calculations. The most common ones are XCOM. It's an American tool, like a database, web database for some results. So you will insert the mixture of material you want, and it will calculate everything for you. FX is like a Filipino one, and 5X is a Turkish one, and it's the most new one. They publish it, I think, by both university. But we have something more advanced and more better, and we try to create something like that, but with different principles in our article. It's called Monte Carlo simulators. Monte Carlo used for different applications or complicated applications in mathematics for simulation, but Gen4 and MCMP are dedicated for the field of radiation physics and radiation shielding. So our topic is AI and radiation shielding. So what's the use of AI and radiation shielding? First of all, it accelerates the material discovery, because if you have already prepared a good model, so you can prepare materials faster, and you can have new ideas or faster ideas and insights about the new materials. Enhanced performance of prediction. You know, in Monte Carlo, for example, if you can try to make some simulations for some materials, it takes time and it needs a good computers. Also, you need work with Linux. It's not easy for everyone, and it's not easy for all technicians and doctors. So it's easier to have a small model. It can work on Google Colab as a cloud, and it will work something very easy. So after training, which will take a lot of time, it will be very easy to use. Finally, it's cost effective, because now you can use it with a mobile application, so it will be easy and cost effective. Our research objectives and justifications. First of all, significance of radiation shielding properties in general, because we have to focus in this field. Importance of bioactive glass, is this material, there's a lot of literature about it, but not focusing about radiation shielding. Also, AI transformative role in material science, that finally it's a material science, so using AI in material science, AI as a trend, and material science as a very important science, that would help us in creating new materials easier and faster. And last but not least, gap in literature. When I was looking for literature for this material for another research, I found out that not many articles studied the Bioglass and its applications in the radiation shielding and AI. So I tried to fill that gap. Okay, we finished the introduction. I hope that topic now is clear. Let's speak about the materials and what we did in the article. Oh, the colors is not clear. Okay, no problem. This study investigates the main relationships. You know, machine learning is the relationships between different elements. Even if we are not understanding those relationships, but computer will understand it and give you results. So, relationships between the molar fraction of the material that we mentioned, density, energy, and mass attenuation coefficient in the Bioglass that we chose. The inputs of the machine learning model will be molar fraction, density, energy, and the output will be the mass attenuation coefficient. We can understand that from better from the abstract. First of all, you can see here we have the inputs of the model. We have the energy. Energy will be in the mega electron volt because we are speaking about medical radiation, shielding for diagnostic and therapeutic. So sometimes it will achieve 15 mega electron volt. That's our limit in study. Also, we have the molar fraction for the material we choose, the Bioglass, or contains silicon oxide, sodium oxide, calcium, and so on. Also, we have the density for materials because it's important. Generally, it differs and it uses for some calculation inside the properties like a cross-section for the material, so it's very important. We will apply some models, we'll discuss it later, and those we will compare the results to find out which model will give us the best results in the mass attenuation coefficient. That's our aim for studying. So now, in machine learning, the most important thing is the data set. Preparing the data set was very difficult because it's not available online, it's not public. So that forced us to do it by hand, crafted precisely inside our lab. So we started using, most of our work was with Python. So started with Python, creating some random values for the fractions to avoid overfitting or underfitting of the results. We created this data set, and I gave you a sample to understand it, because this is the data set that entered or feed it to the model. I feed it to the model. First of all, the energies, different energies, they range from 0.0 or 15 kilo electron volt to, it's not clear here, but we will discuss it later also, 15 mega electron volt. So it's a big range of energies. Fractions for materials, the density for each material, and the mass attenuation coefficient. This is a statistical demonstration to understand our work, our data set, sorry. So in energy, we have let's see, this is the minimum. The minimum value was 15 kilo electron volt, and the maximum is 15 mega electron volt. And we have a lot of densities and mass attenuation coefficient, which is the aim of our study, and the fractions for the mixture of our material. Also, another statistical graph which will help us to understand something very important. You can see this is called Pearson correlations. It says that it will represent the correlation between elements inside the data set with numbers. So if the numbers around zero, means there is no correlation between those elements. They are not affecting each other. If there is something close to -1, means it's inversely correlated. And if they are in positive and close to 1 or 1, it means that they 100% correlated normally. So as we can see, we have two elements, the dopants of our work. Those ones, lanthanum and selenium oxide, are really affecting the data set or correlated with density and correlated with other things because they have a very high density, but other elements are almost balanced. So let's start about the calculation. How did we calculate that data set? We used this software called EPICS. It helped us to find out the reference mass attenuation coefficient for the random values that we created. Then we applied our machine learning models. We applied about 15 models, as I remember, from different fields of machine learning. In machine learning, there's a lot of principles, not the same. So we applied ensembled learning methods, which means it's a method that uses different principles of machine learning inside itself, and finally sum the final results to find a better prediction. And we of course discussed that because it's a very important point later. And non-ensembled learning. In ensembled learning, we use random forest, extra trees, gradient boosting, and cat boost, and so on. In non-ensembled, we use the basic linear models and the basic distance-based models like vector machine and k-nearest neighbor. So now we have the data set. We found out the results out of our model, but we need some evaluators outside of our work to say that our work is fit to something that is high quality or not. So we use two tools, and I mentioned that before. The first of all is the Monte Carlo simulator, which is called Gene4, and the second one is the same EPICS, but the most important tool is the Gene4. This is the EPICS, but this is Gene4. It's an environment, works in the Linux environment. It's a tool works in the Linux environment. It's used in the radiation shielding and radiation therapeutics. Also, we use something to evaluate our methods, two main principles. First of all, we use something called k-fold cross. It's a tool, or generally it's an evaluation principle used inside, or not evaluation, it's like checking in principle, used inside the models to check that, generally in machine learning, let's express that. We have two data sets inside our data set. We have something data for training the model, for giving them the information, and the last one, or the last part, the smallest part, will be for testing. To say, okay, I gave you some data, I want to check you are not memorizing, you are expecting something new or prediction for something new, so you have to choose something else. So you use test data. But sometimes we have a problem because testing data maybe contains some important data I want to train model for. So I will train model 5 or 6 times according to number of K that I used. Here I used 5. I trained it 5 times, but I separated the data to 5 folds. For example, in first fold or first iteration, I trained the model with the first 4 parts and tested on the 5th. In the second one, I used the 4th one as a testing. In the third one, the third one as a testing, and so on and so on. So the model now exposed for whole data and tested for whole data. So it's better. It's generally a general tool used in machine learning to check that the data set is totally used. And finally, generating evaluation, we have something called in machine learning evaluation metrics, like errors, calculating the errors, but we have different principles, like mean absolute error, mean square error, root mean square, and R square. We finished now the results. The methodology. Let's speak about the results. Okay, I know the table is not clear, and even me, I wasn't able to understand it very easily, so it needs a lot of time for reading and analysis, but I can summarize it like that. I don't know, maybe it's not like this. Okay, generally. First of all, the name of the model. We have all the models that we have chosen. The first error, mean error, the mean square error, the root mean square error, and the R square error. Let me speak in a simple way. All the errors should be closer to 0 to be in the best. So if the 0 is the best, is the ideal, which is impossible. And the R square should be 1, which is the ideal for it. So if the model is closer to 1 in R and closer to 0 in others, means it's the best. So we have the decision tree, the random forest values, but there's a problem here, I don't know in the editing, and the cat boost, the last one, the cat boost here, this one. So they were the best, because they have a very low errors and a very high R square. You would ask me about the decision tree. It has zeros and ones. In machine learning, that's called overfitting. Means the model somehow memorized the result. So if you tested the results in another results out of the data set, in another data out of data set, the result will be very bad, because it's only memorizing what you gave him, not predicting something new. So the relation created according to the data set is useless. Real application comparison. Yes, out of literature, I found out someone who prepared this material in the laboratory and gave us a real-life study and real-life values and fractions. So we have 5 types or 5 samples with different fractions, as you can see. Those are really applied and created in Ershad et al. With Ershad. And I tried to apply my model, the best model, which was the cat boost, on these details. Not clear very much, but this is the first sample, the second sample, 4th, 5th, and 4th and 5th. You can see here, those are the results from EPICS, from Gent4, and from our model, to compare them. This is the same. I know it's not clear, so I draw something for that. Let's speak about the first one. This is the first sample. The first sample, the blue line is our model, our AI machine learning model. The green one is the Monte Carlo simulator, and EPICS is the red one. But let's speak about the green one and the blue one. You can see there is a good agreement between both two lines, except in this area. We will discuss that in the results also later. Also, this is the second, the third sample. Yes, this is the third one, and this is the fourth one. So you can see, in general, we got a good results. So, almost finally, let's speak about discussion. Comparison of mass attenuation coefficient. Sorry, I haven't mentioned that. This is a relation between the mass attenuation coefficient that we discussed before. It's the most important property to compare between materials and between the energies, from all the energies that we have. So in discussion, mass attenuation coefficient graphs compare the mass attenuation coefficient of different Bioglass systems using machine learning models, Gent4 and EPICS, that we have used. We have also a simple result, which is like fundamental idea that across all methods, mass attenuation coefficient decreases with increasing in photo energy, which means our model working on the same trend of the normal application. Okay, now let's speak about the results. In low energies, we had some errors, higher errors than other energies, like the machine learning model predicts higher mass attenuation coefficient than GENT4, which is the golden reference, as we can say it, indicating potential of sometimes of overestimating. But the overestimation also continues in intermediate energies from 0.08 megaelectron volt to 0.15 megaelectron volt, although prediction being aligned more closely with the GENT4. But the most important thing is that in high energies, means in the therapeutic and, for example, in CT, the energies or high energies, the machine learning model predictions are in good agreement with the GENT4 and EPICS, demonstrating effective performance in capturing the attenuation trend and the correlation between the results of our model. Elements of our model. Simple things like a recommendation, it means refinement. The data set should be refined and created some maybe bigger data set, contains more elements, considering something else, maybe considering the cross section, so we can do it in the future studies. And overall, the performance of the model shows strong performance and accuracy in the medium and high energy scenarios, though adjustments are necessary for future works. The conclusion. Very important points just to focus on. Demonstrate enhanced radiation shielding potential for this Bioglass. Integrates machine learning with traditional simulations. It's a new topic, including Monte Carlo simulation, so it's something new to add to the literature. Achieves high accuracy in predicting mass attenuation coefficient, especially in the higher energies. Validates effectiveness of ensemble machine learning. As we mentioned, cat boost and random forest were the best, and both are ensemble machine learning principles. So we can say that, like a recommendation, anyone who wants to work in radiation fielding, without trying, he can use, or without doubt, he can use the random forest, cat boost, or any ensemble method. Mostly he will have, or they will have a good result. Builds a comprehensive data set, which was very difficult and took a lot of time of us, for total attenuation coefficient calculations, establish a robust methodology for such a research, and finally provides a foundation for advancing bioactive glasses and innovations in material science. Thank you very much.
Çok teşekkür ediyoruz. Şimdi benim için çok alan dışı bir konu aslında, sağlıkçıyım ben, ama diğer taraftan da baktığımızda bu birçok hastalıkta tomografi üst üste kullanamamız, belli sürenin geçmiş olması ya da bazı durumlarda hiç kullanmak istemememiz gibi maalesef tablolar oluyor. Bu tip teknoloji çalışmaları olacak ki bizler o alanda da bir ilerleme kat edebilelim. O yüzden çok kıymetli, çok emekli bir çalışma. Çok teşekkür ederiz. Sunumunuz için de çok teşekkür ederiz tekrar. Sorusu olan arkadaşım varsa lütfen. Buyurun.
Siz gerçekten çok iyi bir sunum yaptınız.
Thank you.
Siz Bioactive class demiştiniz. Bioactive class yani siz orada bir doping yapmışsınız. If I can put in English, you made doping on the Bioactive class that you used rare methods like traditional methods. Like
I didn't know the question.
You use cerium oxide and lanthanum oxide. Why you use these methods?
First of all, both methods are used in implants. So generally, when I use Bioglass for new implants and you making the implants biocompatible, in the literature, I found out that those materials are commonly used. First of all. Second, I have a real experiment about that. It was a part of our work. So we created that material in our laboratory, and we tried to get some results from real experiment and to compare it with this machine learning model. But unfortunately, the time wasn't enough, so I continued with simulations.
Okay. So, do you find the refractive index of this Bioactive glass and the penetration values of alpha, beta, and gamma rays?
Not important if you have the mass attenuation coefficient.
Like you are talking about the radiation, so...
No, not important, because if you speak about mass attenuation coefficient, it's enough. It's a good point. What's Monte Carlo simulators? It's like, how could I say it? It's like to create simulation by giving samples or random samples. So, for example, what simulation did, something like related to what you said, giving like 10 millions of radiation photons, okay? And trying to study each one one by one, the behavior for each one by one, okay? So after that, it will consider something not related to refraction index called, what's called? Cross-section. I mentioned that before. Cross-section, it's very important to say the probability of interaction between the atom and the radiation. So it's something close to what you mentioned, but what we use in Monte Carlo simulator generally to consider something else. Because refraction generally, good idea, but not understanding the atom level. So we're speaking about something else there.
Okay.
Buyurun.
You said about the bioglass, lengthening oxide and ceramic oxide. So is that readily available in our environment, and how did you collect that for your experiment?
It was ready, we bought it.
You bought it?
Yes. Not me, the laboratory bought it generally. But not prepared here in Turkey. Generally, we're preparing things, our professors, or we are in collaboration. I'm Sakarya University of Applied Sciences. We're in collaboration with Sakarya University. Their laboratory has some, another collaboration with Pakistan, India, Malaysia, I think, and Thailand. So they're preparing something there. I'm giving them an order, I need this material, and they prepare it and send it by email, by post.
Oh,
Okay, thank you for valuable presentation. The question is, in the performance matrix,
Okay.
you have choose only 4 different matrices.
Yes, that's
Like preparation,
general evaluation. Yes, you're using those.
What's the reason behind that?
What?
What's the reason behind that? The reason?
Generally, when you study a topic, you will look for a previous literature and find out which is the most important points to mention in the results. So mostly in the results related to regression models, we use, let's speak, in machine learning we have classification and regression. In classification, which parameters we use? Maybe what's called F1 index, accuracy, precision, something like that, so on. But in regression, generally they use those 3 types of errors, and maybe, of course, there are another, but there are enough, and R squared. They will give you enough understanding of the behavior of the model.
Okay, understand. I have another question.
Mm-hmm.
And you have 3 different outputs, right?
No.
So, how much you have the output?
So I have 15 models. I applied 15 models. Yes.
The prediction models.
The prediction model is one. No, the last one, I chose the best one, which is the cat boost, according to the evaluation metrics, of course. And I applied the results according to that.
No, the question is not that. You have first the input data, right?
Sorry, what's input? Yes, we have
Input
input.
data. After that, you analysis and you are using the machine learning models. After
Yes.
that, you get the output. How many outputs you have? If you have, I see only 3 outputs. If you have that 3 outputs, and also
No. Generally, if you speak about number of outputs, it should be 1. The mass attenuation coefficient of the material.
And the question is, if you have only 1 output and you are predicting 3 different models, like carbon forestry and the other 2, and which is the best one?
The best one?
Yes.
I mentioned that. The best one is the cat boost. Why? Because the error is the lowest,
Yes.
and the R square as a something other element, evaluation metric, is the highest. And it's not under overfitting or underfitting.
Okay, I have another question. In the last question,
Okay.
in the iteration process,
Mm-hmm.
you have mission.
Yes.
Is there any criteria you have? When you meet that criteria, you will stop the iteration, or the iteration?
No, that's another approach. Yes, it's true, but because my data set is small, so I have enough time and I have enough resources for that. So it's no problem to scan the data set once, 1, 2, 3 times, no problem. So I have the time, I have the resources, so it's enough. And it's generally it's better when you have to stop the model. That normally happens when you have a very big data set and needs a very strong computer. So say, when I got a good results, stop. But it's not a good approach all the time, because sometimes you will stop in a point, the model will memorize something, not predict something, and we will miss a very important points, because you don't understand what's happening inside the models. So when you have a small data set, it's better to expose the model for whole data.
It is okay, but the question is like, if you are not stopping early,
Mm-hmm.
the last result, it it's not going to be good maybe sometimes.
Exactly. So means the models are not enough. You have to change your work. If you export the whole data for the model, and you have a very bad results, that means your work is wrong, or you have to modify something. You have to modify the data set. You have to choose another models. Because of that, I applied that for 15 minutes.
Not that. If I get the result early.
What if I get what?
If I get the result early, I need to stop. I don't want you to continue the iteration process.
Why?
I get already the result early.
That means you make a model to memorize something, not to predict something, because you have a data set. The data set should be distributed in somehow that demonstrates something. The whole data set, not a part of it. Understand me? So you have to expose the model for the whole data set. So for example, if I have the simple example for machine learning, cats and dogs, something not related to that, but cats and dogs, I want to classify, this is cat and this is dog. So I have 50% of cats images and 50% of dogs images. Okay, and I expose the model for 50% of data. And for some reason, 50% was cat. And he said to me, the prediction for you is 100% because now he's evaluating the prediction of cats. Now when I put dog, mostly he will give me a cat result. You understand me? So it's better if you have small data set or not very big data set, or you have time and resources to expose the model for the whole data set and to find out the problem if you have errors. That's our approach.
Doktora mı yapıyorsun?
Evet, doktora yapıyorum.
Sonda mı yazdınız?
Yok, yeter bir sınav kaldı.
Daha başladınız.
Evet. Teşekkürler.
Çok teşekkür ediyoruz size tekrar sunumunuz'a ve çalışmanıza. Sizi yerinize uğurlayalım ve diğer konuşmacımızı davet edelim o zaman.
Teşekkürler.
Çok teşekkürler.
Flash.